Okay, so let's keep going on like this. So next we'll show that the statement 2 implies the statement 3. Okay, so what was statement 3? It said, let's go back to the statement of the theorem. So statement 2 is of course that there is a unique path. Statement 3 says G is connected and has one more vertex than edges. Now G is connected is of course obvious. If you assume 2, that is you assume there is a unique path between any two vertices, then of course G is connected. That is more or less the definition of connectedness. So the first part of what we have to prove is clear. So let us do this. We assume there exists a unique path. So we are given 2, we need to prove. So let me just state what we want to prove. We want to show two things. One is that G is connected, and secondly that it has mod V equals mod E plus 1. Okay. Now out of these the first part is clear. Okay. So we want to show G is connected. This follows directly from 2. Okay, and what was 2? That there exists a unique path joining any two vertices. So this is just definition. So all we have to prove now is really the second portion of this statement. We have to show that mod V equals mod E plus 1. Okay. Now to do this we will, this is an interesting argument again, we will argue by induction. Okay. So often many statements of graph theory end up needing induction for their proofs. So we will prove this by mathematical induction. Okay. Now what do we mean by prove this by mathematical induction? So the statement I am going to prove is that if I assume 2, that if there exists a path joining any two, there exists a unique path joining any two vertices, assuming that, I will prove that mod V has to be mod E plus 1. This is what we are going to prove. Okay, and we will prove this by doing mathematical induction. So in order to do induction, we need to sort of have some number on which we are inducing. We are going to increase that number slowly and then to see what will happen. Okay, so we will just do induction on the number of vertices. Okay, so let us call n as a number of vertices of our graph, and we will try to prove this statement by induction on n. So what does this mean? So let's do this slowly because it's sort of a new application of induction. So what this means is, so let's see what we will have to do. We will first have to establish the base case of the induction. So we have to first establish what we have to prove for n equal to 1. Now what does that mean? It means you take any graph satisfying the hypothesis 2, okay, any graph with this property and such that it has got exactly one vertex. Okay, take all such graphs. For all such graphs we have to show that this is true. Okay. So let us see what are all the graphs with n equal to 1. Well, that is just the single point, right? N equal to 1 means a single vertex, and so there is really only one such graph. Okay. And in this graph, well, firstly, does this graph satisfy this hypothesis 2? It says between given any 2 points has a unique path between them, but here there are no 2 points even that you can take. So it sort of just satisfies the hypothesis 2 just vacuously, as we call it. You do not really even need to check the hypothesis. Okay, so I have a graph with a single vertex. Well, what's mod V is 1, it has got 0 edges, and therefore this satisfies mod V equals mod E plus 1. So the base case is established. There is only one graph and that satisfies the required condition. Okay, so now the base case is done. So next we have to make the induction hypothesis. So in our case what we will do is use strong induction. Okay, now what does that mean? So here is the strong induction hypothesis that we are going to make. Assume that for all graphs satisfying the given hypothesis 2, that there exists a unique path between any two vertices, and with number of vertices less than or equal to n. Okay. For any such graph, it is true that mod v equals mod e plus 1. Now that is going to be our strong induction hypothesis, and then what we need to do is to show that the required conclusion also holds for any graph G with n plus 1 vertices, okay, and which satisfies the given condition 2. So this is what I finally want to do. Okay, so let us see how would we go about doing this. So let us look at our graph G. It has got n plus 1 vertices and it satisfies the given hypothesis 2, right, and what was the hypothesis? That given any pair of points has a unique path between them. So maybe there is a path between these 2 points, there is another one between these 2, and so on. Okay, so this is maybe what the graph looks like. Now in order to do induction, typically how does one proceed? You have an object which corresponds to n plus 1, somehow there are n plus 1 vertices. In order to use the induction hypothesis, I must somehow construct from this a graph which has got n or fewer vertices, okay, for which I know the conclusion to be true, and then use that to somehow show the required conclusion for the graph with n plus 1 vertices. So let us try and see how to somehow construct a smaller graph from this given one. So what we will do is the following: we will just pick any edge of this graph. Okay, so let me pick this one for example. So pick, let's call it E, any edge of G. Let's call it E, and let's assume the two ends of E are called A and B. The two vertices are A and B. Okay, pick any edge. Okay, and now what we are going to do is the following: we are going to remove that edge from the graph. Okay, so we will delete that edge. Okay, so let me just delete it for now. So I delete that edge E, and the new graph that I form I will call as G hat. Delete the edge E. Okay, delete only the edge, do not delete the vertices A and B themselves. Okay, and let G hat be the resulting graph. So you delete this edge E from the original graph, and the new graph that you get, let us call it G hat. Okay, now what is G hat therefore? Observe the vertex set of G hat, let us call it V, maybe let me call it V hat and G E hat. So let us call the new vertex set as V hat and the new edge set as E hat. Observe the vertex set does not change because we did not delete any vertices. The edge set has one fewer edge. So from the original set E, I have to remove this edge E which I deleted. So that is my vertex set and edge set. Okay, now what can I say about this new graph that I have obtained? Observe, at least in the picture that I have drawn, that the new graph actually splits into two pieces. Okay, so this is, here's one piece and there is another one. Okay, so this is how it will always happen. These are what you call the two connected components of this graph G hat. So let us define formally what these two pieces are, right? How do I get these two pieces in a formal mathematical way, in a precise way? So these two pieces are defined as follows. So let me just say, let's call it VA. So, I am going to define two new vertex sets. V corresponding to the vertex A is all those vertices of the original graph such that there exists a path from, so I mean this should really be thought of as in G hat, there exists a path from A to V in this new graph G hat, okay, and VB hat is all vertices such that there exists a path from B to V in G hat. Okay, so I have defined two subsets of my vertex set. So, my first subset is all those vertices which you can reach from this vertex A by a path which is in G hat, okay, which means without using this deleted edge. So, that edge is not there anymore in G hat. Without going through that edge, I should be able to go from A to my vertex V. Okay, and what are such vertices? They are exactly the vertices which are in this in this left hand side portion. So, I take this, I divide it here, and all vertices which lie here are what form VA hat. Those are the vertices. Likewise, the vertices on the other side are the ones which you can reach from B. So, we will call this VB hat. You can reach those vertices from B by following paths which do not involve that deleted edge. Okay. So, I have split my graph into these two pieces, and so I will think of these as two subgraphs. So, I will take all the edges as it is. Okay. So, now let us look at EA hat is edges, set of all edges in G hat between the edges which go between two vertices of B hat. Okay, so, edges on the left hand side of that diagram which I drew, and likewise EB hat will be edges in the right hand side, the right hand portion, the edges which go between any two vertices of VB hat. Okay, now having done all this, we have succeeded in defining two smaller graphs. So, what are our smaller graphs? The left hand side portion and the right hand side portion. So, let GA hat denote the graph with vertices VA hat and edges EA hat, and this is the other part. Okay, so this is really the key induction step where we have broken the bigger graph into two smaller graphs. Okay, and observe these new graphs actually have fewer vertices than the original, right, because A is only in this graph GA hat, not in the other one. Similarly, B is in the other one, but not in this, right. So, at least one vertex is missing from each of them, and so now I can apply the induction hypothesis provided these two graphs also satisfy the property 2. Okay. So, here is the key observation that we will make. We can actually use the induction hypothesis on these two graphs. Okay. So, the observation is that, so the key observations may be both these graphs have strictly smaller number of vertices than the original. Okay. So, that is clear because at least one is missing, and secondly both graphs satisfy that hypothesis 2, satisfy that property 2. Okay. And what was property 2? It said that i.e. there exists a unique path, there exists i.e. there exists a unique path joining any two vertices. in the graph GA hat, okay, and likewise similarly in the graph GB hat. Okay. Why is this true? Well, because the graphs GA hat and GB hat are actually just parts of the original, right. So, in this graph I want to prove from A to V there can only be a unique path. Okay. Suppose there were two different paths in this graph GA, then those two different paths would have also been in the original graph G, right, but the original graph G had only a unique path between these two guys, right. So, because these are subgraphs of the original graph and the original graph only had one path between 2 points, the subgraph will also have the same property. Okay. So, this is clear. Why? Because GA hat, GB hat are what we would usually call subgraphs or induced subgraphs of original, and G satisfied that property too. Therefore, the same property is inherited by the subgraphs. Okay, good. So, all this elaborate setup was so that we could use the induction hypothesis. So, now let's actually use the induction hypothesis and see what we get. So, here are two smaller graphs, they have fewer vertices than n, less than or equal to n, and they satisfy the hypothesis too. So, we can use induction. So, by the induction hypothesis, what we conclude? We conclude that the number of vertices of this graph is equal to the number of edges plus 1, number of vertices of B is number of edges plus 1. Okay, we get. Okay, now that's almost all we need. Using this, we will prove what we want. Okay, so let's add these two equations. Number of vertices of VA hat plus VB hat is equal to number of vertices of EA hat plus EB hat plus 2, so which I will write as plus 1 plus 1. Okay, so this is the equation that I conclude by adding these two. Okay, so that completes the induction step. So, we have added this equation and we conclude mod VA plus mod VB equals mod EA plus mod EB plus 2. Okay, now here's the key observation. So, let us look at the left hand side, which is mod VA plus mod VB, and so I drew that diagram in a certain way. I claim VA and VB are two disjoint sets. So, firstly VA and VB, V hat B are two disjoint sets, so their intersection is empty and their union is the whole. Is the full set of vertices. So, this is the first claim. Okay. Now, why is this? At least the picture had exactly that, suggested that VA somehow is all vertices on the left hand side of the picture, VB is all vertices on the right, but sometimes pictures can be misleading. So, we have got to be careful when we write arguments. Why is it true, for example, that the set VA hat and VB hat are disjoint from each other? Okay, so, let us prove that first. So, what was the definition? VA hat is all those vertices where you have a path from A to that vertex in G hat. VB hat is everything which has a path from B to that vertex in G hat. Okay. So, if suppose these two sets were not disjoint, so let us do that. If VA hat and VB hat was non-empty, let us take a vertex which belongs to this, let V be a vertex in the intersection. Now, what does that mean? It says that I had A, I had B, and I had that deleted vertex E from G hat, and what I am assuming here is, here is my vertex V such that there is a path from A to V which does not involve that edge E, and there is a path from B to V which does not involve that edge E, right. So, because I have said there is a path in G hat. Okay. Now, let us look at what this will imply. This will tell us that there are in fact two different paths from A to V, because on the one hand the path that we had here, we know for sure it does not contain the edge E. Now, we can manufacture another path as follows: you first go along E and then you take this other path here. Okay. So, this is really the argument. Let V belong to this. So, let us then, there exists a path from A to V which does not involve, which does not use the edge E. Okay, that is because V belongs to V A hat. Similarly, V belongs to V B hat. So, we conclude likewise that, and there exists a path from B to V which does not use the edge E. Now, what we will do is, to this path we will just adjoin, we will attach the edge E to this path. So, now consider a new path. So, attach, let us call this path as something pi 2, this path as pi 1, let us give these names. So, attach edge E to pi 2 to get another path in the original graph from A to V. Okay. So, this contradicts the assumption that in the original graph there is only one path between any 2 points. Okay. So, this contradicts the assumption that G satisfies the given condition 2, that between any 2 points there is only a single path. Okay. So, that proves what we want. So, therefore, we proved the first part of the claim, right. So, what is the first part of the claim? That the intersection of these two is empty. Let us prove the second part of the claim. Why is it true that the union is every vertex? In other words, why can you given any vertex V, why is it true that there is either a path from A to that vertex or a path from B to that vertex which does not involve the edge E? Okay. So, the proof is almost the same. So, given, so this is now, let us prove the second part of the claim. So, now I will just show V A hat union V B hat is the entire vertex set, and to do this we will look at two cases. So, given any vertex, we know the following: there exists a path from A, right, from the vertex A to V. In fact, there exists a unique path from the vertex A to V. Okay. Now, either this path, so there are two cases. So, case 1, this path, so let us call this path pi uses the edge, this path uses the edge E. Okay, or let us say for maybe case 1 is pi does not use the edge E. Okay. So, suppose pi does not use the edge E, then what does it mean? It tells you that from A to V, so here's B, this is my edge E. So, from A to E I have got a path, from A to V I have a path which does not go through E, therefore it is a path in G hat. Okay. So, in this case it is clear that this means pi is in fact, you can think of it as a path in the deleted, the smaller graph G hat where E is deleted. This means that V is in VA hat by definition, because VA hat was exactly all those vertices which can be reached from A via path which lies purely in G hat, which does not involve the edge G. Okay, so case 2, what if pi involves the edge? Pi uses So, if there is a path which uses the edge E, what will that look like? So, first you go along E and then you go along some path, right. So, first E and then some path. Then what does that mean? It means I can get a path from B to V which does not use the edge E again. Okay. So, remember, a path means I cannot repeat any vertex or an edge again. So, if there is a path which starts at A, first goes through E and then goes to V, I just delete E from that path and I will get a path from B to V. So, we are just using the definitions of these terms like path and so on very carefully. Okay. So, pi uses the edge E, then let pi dash be the path pi from which E has been deleted. So, we could write it in the notation for paths if we wanted to, but you just write down that sequence of vertices and edges and then remove the first vertex A, remove the edge B from that path, edge E from that path, and then it will just be a new path which starts with B, another edge, another vertex, edge and so on. Okay, so that new guy is what I am calling pi prime. Then observe, pi prime is a path from B to V, and since it is a path it can't use the same edge once more. So, it is a path in G prime. And what does that mean? It means that this vertex V belongs to the set VB prime. Okay, so, we have shown in case 1 the vertex is in VA prime, in case 2 the vertex is in VB prime. So, the union of VA hat and VB hat is in fact the entire vertex set. So, again we have proved our claim. Okay, so now we are more or less ready to finish the proof. So, recall what was the definition of the edge sets now. So, where were we actually use the induction hypothesis to conclude this statement that VA hat and VB hat and edges between them EA hat and EB hat, that these relationships hold between the numbers of vertices and edges, and now we were able to add them together to obtain this fact that VA hat plus VB hat is equal to EA hat plus EB hat plus 2. But now the left hand side, which is VA hat plus VB hat, we have realized this is just the following, it is equal to the total cardinality of V, right. Why? Because of this claim, because VA hat and VB hat, their intersection is empty and the union is the whole thing. So, the total sum of the two cardinalities, so this is sometimes what we call a set partition. We have got the set V which we have partitioned into two disjoint subsets. So, the total number of elements of VA hat and VB hat will exactly be the cardinality of V. Now, if you look at the edge sets, the edges of EA hat and EB hat are just edges which go between the vertices of the respective subsets. And let us look at this diagram again. The only edge that is missing from EA hat and EB hat will be this one edge which connects A and B, the original edge E that we had. So, this edge E is the only edge that is missing from this calculation. So, the cardinality of EA hat will account for all these other edges. So, all these edges here, likewise the edges on the other side, they are all being counted by cardinality of EA hat and EB hat, and so we conclude that EA hat plus EB hat plus 1, this one extra edge, that will be exactly the cardinality of E. Okay. So, if we put this together, what have we established? We have established, so we have shown that cardinality of V is cardinality of E plus 1. Okay, and that is exactly what we intended to prove. So, this completes the proof that 2 implies 3. Okay, so, what we have shown that the statement 2 implies the statement 3.